told me already this was 12 Leibniz. 12 Leibniz, in theory.
So where's the camera for the video conference? It's just in.
Computing Center Stuttgart here. We just signed a memorandum of understanding, the School of IT and the School of Engineering, where also HPC Center belongs to, and also Academy of Architecture and Urban Studies, why we think this is a good location to have the presentation of Michael in this kind of joint venture. And yeah, Michael has been the director since many years of High Performance Computing Center in Stuttgart. HLRS is one of the 3 supercomputing centers, or kind of federal supercomputing centers of Germany. Same time, it's a computing center for the University of Stuttgart. Attached is the Institute of High Performance Computing, where Professor Resch is also the head of. Yeah, I will keep it short, I promised.
Thank you.
I give the word to you, and we are looking forward to your lecture about potential of HPC and AI.
Thank you very much, Fabian.
Thanks a lot.
Thanks for inviting me here. Thanks for the kind treatment here. I'm happy to be here. Thanks for you coming to this presentation. I was told that you don't care how long I talk, which is dangerous, but I'll try to keep it down to 45 to 60 minutes or so, and I'll probably be quicker if you look boring and slower if you look interested. So it depends on your face's expressions what is going to happen here. Yeah. As Fabian said, I'm the director of a supercomputing center. My background is mathematics, applied mathematics, and this is how I entered into that field. And the Stuttgart University itself is a place where it's a technical university. It calls itself university. It gave up the title of technical university like 40 years ago or so. But the University of Stuttgart is very close to reality in a sense. So there is some discussion sometimes whether we are too close to industry, but I think it's a good place to be. Now what I will do is, if this one is talking to me, no, it doesn't want to talk to me, that's okay. I'll first introduce the center because it gives you a rough idea of how I'm looking at things. Because I will talk about HPC later on and AI and the usage of HPC and AI, but you should get some understanding of the background that I'm talking. Well, basically being a supercomputing center usually means, okay, you run a system and you let people use the system and you do the accounting and everything. And we say our focus is on computational science and engineering. So we're not focusing on a machine, we are focusing on the solution. And that means we bring in more fields than the traditional HPC. I'll walk away from this. We do support researchers. Being a German national center, we decided that having 3 national centers, we need to have some specialty. Yeah? Now, the specialty of Stuttgart is famous for what? Does anyone know what Stuttgart is famous for? Never heard about it? Yeah? Art? Cars, thank you. I was surprised to hear art, yeah. It actually is famous for art, yeah, because we have an excellent ballet and we had some interesting artists. But yeah, it's cars. It's cars. So our focus is on engineering, yeah, because we have huge engineering departments, mechanical engineering, civil engineering, and everything. And we said, okay, we are the German center to be focused on engineering applications and also on what we call global system science. This global system science sort of came from what we did in engineering, because we saw that we were gradually moving away from the pure technical things into the collaboration with some other fields. And because we are in engineering, we work with industry. That means we provide solutions to industry, we provide access to our systems. We're the only center in Europe that is open to industry to the full extent and is selling CPU cycles to industry. Last year we sold 300 million core hours to industry, about 70 companies. The largest one of them being Porsche, the other car manufacturer, which I cannot afford, yeah. I cannot afford Mercedes, I cannot afford Porsche, so it's bad to live in Stuttgart, yeah. But then what we figured with our research in engineering and global system science is that what is happening here when you do computational science and engineering is spilling over into the fields of society and politics. Yeah? Some of you may have heard about climate change. Raise your hand if you haven't heard about climate change. Yeah? So why do we know about climate change? The answer is computer simulation. There is no other way for us to tell what's going to happen in the next 50 years with climate change other than climate change simulation. And there is a variety of fields where simulation, computer simulation, is slowly moving into fields that are no longer purely technical. Like we are using computer simulations in medicine. That means we are no longer just people who say, okay, I'm running a job here, I'm doing some kind of Navier-Stokes equations for the flow of something, I'm doing some kind of finite element methods, I'm writing a paper and I'm publishing this, and everybody says, wow, great, it's fantastic, new method, blah, blah, blah. We're talking to doctors, and they ask completely different questions. They don't ask what is the rate of convergence, or what is your mathematical method, or which system did you run it on. They say, is it correct? Now the answer is it correct is difficult to say, because we're working with a digital machine. And a digital machine is a digital machine, which means it is only digital, not analog. And being digital, you probably think that a computer is giving you always the correct results, but just give him the right problem, and he's going to give you the wrong result. Keep in mind that a computer is unable to divide 1 by 3. Because this is not the number that a computer can represent. And you might say, okay, it doesn't have an impact because I have, I don't know, 26 digits or something like that, and that's good enough. Yeah, that's true. Unfortunately, it's not true if you continue to work with this 1/3, and you have a number of these things, and you end up with something that is probably right, but you don't know whether it's right. Now, usually you would say, if it's not right, and I'm a mathematician, if I try to find out whether something is right, I try to give a proof. Now, I can give you a proof for the mathematical method, but I cannot give you a proof for the operations that a computer is doing. Worse than that, computers make mistakes. We're having on a processor something like 1 billion to 4 billion transistors. Yeah? And they are designed by human beings. So there's a map of this processor. The processor is like this. You're working with that, and there is mistakes in that design. Obviously, because it's done by humans. And sometimes people say, no, it's done by a program. But the program is written by humans. The point is, when you write a program, for those who are not familiar with that problem, the estimate is that for every 500 lines of code that you write, you make a mistake. This mistake usually is not visible because if you would see the mistake, you would correct the mistake. But it's in your program. So what is happening here is that we are working with a technology that is supposed to give answers to society and to politics. Especially politicians would like to hear something like yes or no, or 0.5 or 0.7. And you're talking to these people and you say, I'm using this method on this system, using that software, and the probability for this result to be correct is 95%. Now, if you ever want to be hated by a politician, just tell the politicians this sentence. And they'll look at you and say, that's nothing I can work with. I mean, I have these people out there and they want answers. And I'm supposed to give these answers. And that's not just making fun. We have a department, a group of people working on this problem of trying to figure out how we can communicate what we're doing here to a general society and to politicians, because they need it. And at the end of my presentation, I will show you an example which some of you may have heard about already. Yeah. Okay? So that's what we think about computer simulation. It's a strong tool. It can help you fix problems. One of my colleagues is doing water turbines. He recently died. But when he designed a water turbine, this result was like 3% incorrect. And that was good enough, because for a water turbine, that's perfect. And the companies would accept that, yeah? So yeah, it's great there. But this is, you're staying entirely in the technical field. You're never in public discussions or anything. Yeah? So we focused on energy, climate change, health and the aging society, mobility in the 21st century, digital societies, and combinations of these topics. I'll show a small movie afterwards. Yeah? But when you do high-performance computing, you have to do other things. I just had a discussion with your vice president about green IT. Yeah? I'll show a slide afterwards why green IT is important, because it's not so much about being green. It's about being cost-effective. Yeah? A supercomputer is a system that is huge. Yeah, they used to be very small about 30 years ago. We could have put a supercomputer here somehow. Now it's more like 100, 200, 300, 400 square meters. And they have a huge power consumption. I will talk about this later. And we need to do cybersecurity. Now, why do we need to do cybersecurity? Anyone know why we need to do that? Because a supercomputer is a weapon of mass destruction. I'm not kidding here. In the year 2020, practically every European supercomputing system was hacked. It was by accident that we found out. And what happened was that someone took over these systems. And we don't know what the person or the organization who did that actually wanted to do. Because the only thing we found was modifications. But we found no indication what anyone would do with such a supercomputer. Now, if you are in cyber war, you start to understand what's happening there. You take over these computers, you use them as a digital army. Yeah? All the poor Russian hackers that have to pay for nodes and nodes and nodes, if they come to Stuttgart, they get 5,600 nodes for free. They can use them as an army to attack government systems. Yeah? And that's what everybody's worried about. That's why cybersecurity is important for us. It's also important because industry is using the system. That's okay. But the worst case for me is if any Russian or Chinese organization take over my system, use it to attack some government agency in Germany, and the headline of the news in Germany is HLRS system used to attack the Bundesnachrichtendienst. Yeah? That's a problem for us. Yeah? And we're talking AI, but in this presentation I will talk about AI later on. Okay, now these are some of the key performance indicators. We love that because industry people love that. We are now about 150 people. That's 130 or so, plus 20, 25, 30 students. We get some project funding, which is 7 million euro. We do a lot of training. Training means that we educate people who have a degree. Some of them come from industry and need to learn something because their company is moving from experiments to simulation, but most of them are our own users. And we are selling CPU cycles to industry, and last year we sold 2-point-something million euro, which is nice. Now, as a taxpayer, you don't like that because you're paying it my system and I make a profit with that system. So government says you need to take the money and put it back into the system. So we just grow our systems with this money that we earn every year. We run a supercomputer, surprise, surprise. That's our supercomputer. It's just a large-scale system. The basic idea of a how many of you are IT experts? Raise your hands. Thank you. How many of you are non-IT experts? Okay. The idea of a supercomputer is trivial. Yeah, you just take something which has a processor like this, and you take as many as you need, and you just connect them, and you say if they're working together, they are faster. So this system is basically, you have what we call nodes. It's 5,600 nodes. Each node has 2 processors, and you just put them in these racks, and you cable them and connect them, and then you have these 5,600 nodes working on one problem. Now the trick is not building the system, which is difficult. The trick is making the 5,600 nodes work on one problem. Now, how many of you have ever worked in human teams? Everyone. Have you ever tried to convince 10 people to do the same thing to achieve something? Anyone tried? Was anyone successful? Please come to me afterwards. I would love to learn how you do that. It's possible. I'm just kidding. Yeah. But the problem for us is really the same. You have 5,600 nodes, and you should give the same amount of work to these 500-600 nodes to make sure that you actually solve the problem. I keep telling my students that they should think about the construction of a house. So when I was a student, I earned some money working in construction work. Yeah? And so we built a small family house. And the neighbor was also building a house, and he was alone. So I keep telling my students, if you're 4 or 6, it's much easier to build a house. Yeah? But what happens if you're 1,000? Doesn't work anymore, because there is not enough work. Yeah, you can't build a house with 1,000 people. You can build a Colosseum with 1,000 people, but you can't build a house. And that's exactly what's happening in supercomputing is you need a problem that is big enough to require a supercomputer to give every node enough work to actually do something. Yeah? And then you need to synchronize and all these things. Now this one is outdated, and we will move this year to this one here. We gave them code names. Yeah, this one is called Hawk, and this one is called Hunter. And there is a story behind that, but I don't have time to tell all the stories, right? Yeah, okay. So we are moving from CPUs to GPUs. Yeah? The reason behind that is twofold. First of all, CPUs are bad, and second, GPUs are good. Well, the problem is CPUs are not that bad. They just don't show enough improvement. Yeah? And GPUs are not that good, but what they give you is a high level of peak performance and a low power consumption. So the Hawk system was something like 3.2 megawatt, or still is something like 3.2 megawatt, which is roughly 5 million euro or so in terms of costs every year. This one is going to be 0.6 megawatt, which is something like, I don't know, 800,000 or 900,000 euro. So it's going to be much cheaper, but it gives you a higher level of performance. If you had a look at the performance number, Hawk was 26, this one is 40 petaflops. Petaflops is just a number. Ignore it. Yeah? So this will come in, and we will teach people how to work with this for 2 years roughly, maybe 2.5 years, maybe 3 years, and then we will just replicate. And again, you see what a supercomputer is. I had Hunter being this one here, 1 rack, and I have Herder being this one here, I don't know, 20 racks or something like that. That's how you build a supercomputer. And then we will see some peak performance, and it's difficult to tell what's actually going to happen because the market is not so nice with us to tell us everything about the future, especially not code names. And then when you do this, when you buy all these systems, this is what you can do. Yeah? This is some climate research simulation of precipitation. And it even gives the date. This is March. And Tallinn should be somewhere here, yeah? So you see the waves coming in from the west, things like that. So you can do this with a level of detail that is really great. When I saw this like 20 years ago, you see New Zealand here, yeah? New Zealand was not on the map of climate research until about 10 to 12 years ago. Because the resolution of the meshes that you would use to do the simulation were not good enough to show New Zealand. So New Zealand just didn't exist. The people in New Zealand were not that happy about it, but yeah, we still had some results. But now you really can do every detail. And the reason for this is that HPC was giving you this curve here. That's 1993 here, when we started to sort of benchmark the supercomputers in the world. And there is a list which is called the top 500 list. And you have the 500 fastest system in the world. And everybody wants to be very high on that list and then tell the politicians that we gave all the money for a supercomputer, which is now number 23 in the world, or 52 or something like that. Now you're a US president, you want to be number one. You're the Chinese president, you want to be number one. You're the Japanese president, you want to be number one, which is difficult. Yeah? But actually this race for the fastest supercomputer can be seen here. The golden triangles are the number one systems in the world. Yeah? So when you look at this here, this is the Japanese supercomputer, and then there is a US supercomputer, and then there is a Chinese supercomputer. And you may assume that this has no influence. Yeah, it's just for the fun of it, every country trying to have the fastest system. That's not true. The Chinese supercomputer coming in saw a president called Donald Trump. And he said, how can that be? With the Chinese supercomputer being faster than the US supercomputers, and the Chinese supercomputing is US technology. So he imposed an embargo, simply because of this list. So what happens next is, guess what happens? The Chinese government decided not to have their computers on the list anymore, making sure they don't embarrass the US president. Yeah? But what you see here is the speed is improving by a factor. This is a logarithmic scale by a factor of 10, 10, 10, 10, 10. Everything is going well. But what you also see is that this curve, that's the total amount of flops. That's the number 500. And what you see, the number 500 starts to flatten out here. Yeah? The peak system still goes up, and the total amount of performance also starts to deviate from that curve. And what were the drivers for this development? The driver was what we called Moore's law. Yeah? Gordon Moore, famous researcher and entrepreneur, businessman, he died last year, just in time not to see that his law, or what was called his law, is coming to an end. What Moore said, and we are all used to that, especially the older ones, the younger ones not, so most of you are not concerned about Moore's law, but I am, and a few of you in the room still know that. Computers are getting faster over time, right? And they always did, and they will always do that. And that's what Gordon Moore said in a paper in 1965, where he said the complexity for minimum component costs increases factor of 2 per year. That was it. Getting faster at the same cost every 12 months. Later on in the 70s, he modified it and said 18 months. Factor of 2. And that's what we see in these curves. We see exactly this increase of speed. The background of this being that if you have more components, the components are smaller, the distances between components are smaller, so the signal has to travel for a shorter time. If the signal can travel for a shorter distance, you can increase your clock frequency, you can calculate more. Okay? Usually I tell this in 2 hours to my students. You just grabbed the meaning of it in 60 seconds. Congratulations. Yeah? So that was everything that was behind Moore's law. And what we saw over time, and now this is very technical, I'm sorry for the non-technical people, but it's interesting. Yeah? What you see here is transistor count. You need transistors, and if they get smaller, you can have more transistors on the same area. Yeah? So you see the transistor count was going up. This is again logarithmic scale. It's going up, everything is fine. But what is interesting, as I told you, is the clock frequency. And the clock frequency flattened out here around 2000. Now, some of you may have laptops, right? What is one of the features that you're familiar with your laptop? It's heat. It's just getting hot. And the reason why it's getting hot is that if you increase the clock frequency with the current technology that we have, you increase the power consumption. That's the red one. And now the power consumption is at something like 200 watt. So what you're having here is a heating system. with 200 watt. That's nice in winter when it's cold. So Tallinn should have a lot of supercomputers just for the heating, yeah, because it's cold in winter, yeah. But this one here is not so good for the technology. If you increase the clock frequency, which you could do, currently we are working with 2 gigahertz, maybe 3 gigahertz, sometimes 4 gigahertz. But if you increase that to 10 gigahertz, technically it's possible. 100 gigahertz, technically it's possible. The only thing is that the temperature increases to an extent that at 10 gigahertz, you need very special cooling equipment. At 100 gigahertz, unfortunately, after less than a second, the processor has melted away. Yeah, okay, understood? So yes, we can have more transistors, which could make the system theoretically faster, but the power consumption goes up, so that's bad news. Now, if you cannot speed up things, you have already learned how we build supercomputers, and now you learn how we build processors. If you cannot speed up a single processor, you just build 2 processors. So we still have the number of transistors here, and what we can do is we can build 1, 2, 4, 8, 16, 32, and so on, what we call cores. Now a processor actually is not 1 processor, but 8 processors. You keep the clock frequency low, you keep the temperature low, but you still have a factor of 8. That's what we're doing. We are playing very simple games in HPC, I'm sorry to say that. Yeah? And so people are saying, is this going to end? And Jensen Huang, the CEO of NVIDIA, who has heard about NVIDIA? Anyone know that NVIDIA is the most valuable company in the world? Anyone know why? Please come to me afterwards. I don't know why. Jensen Huang said Moore's law is dead, and he said this already in September 22, and when we spoke to him and his company in 23, we learned why. Jensen Huang said, everybody wants our NVIDIA GPUs to do artificial intelligence, so we're going to increase the prices. So what Jensen Huang was referring to was, it's not at the same cost. Dear customer, you have to pay more. Yeah? Okay? Now Intel said, no, 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 no. Everything is going to be fine. Innovation is not dead. We will maintain Moore's law through innovation in process packaging and architecture. Now the idea of Intel is relatively simple, straightforward exercise. I have this processor on an area, and I built 2 processors, and then 4 and then 8 and so on. Now once I have like 64, it's getting sort of narrow. Yeah? So what do? And the answer for every technical guy is go to the 3rd dimension. So we have 32 on one of these dies, and then we stack 2, 4, 8, 16 on top of each other. Great. We get more performance. But as you have already understood now, what else do you get? More power, which gives you more heat. So it's not going to work. It gives you much higher cost. Yeah. So yes, theoretically, and they are referring basically to, what does it say? Keyboard device detected, okay. What they are saying here is, we will charge you more, and what they are saying here is, we'll pretend that it's getting better, but we will have to charge you more because our technology is more expensive. Yeah? So, and then when we look at this number again, what we see is this one here. Yeah. So far we were assuming that Moore's law was giving us twice the performance at the same cost, roughly. But when you start to investigate, you find out that in 1993, a supercomputer was 30 million euro. That's a substantial amount of money, especially if you don't have it and need it. Yeah? And the power consumption was 60 kilowatt. Now we move to the year 2002. The #1 system in the world now costs a factor of 8 more. And 2 megawatt, that's a factor of 30, 35, something like that. We move to this Chinese wonderful supercomputer, and we end up with 400 million euro and with 18 megawatt. And the most recent system is roughly 800 million euro and 23 megawatt, and the #2 system is 38 megawatt. So the #1 is very energy efficient. It's only 23 megawatt. Now what is 30 to 50 megawatt? What is that? That's the power consumption of a small, medium-sized African country. The total power consumption of the 4 or 5 or 6 million people living there. So the number one supercomputer is consuming as much power as 4 million, 5 million, 6 million people in Africa. That's quite an interesting number for me. And the question is it worth doing? Now, when you look into the future, my estimate is that to be the number one in the year 2027, 2028, you will need something like 1.5 billion euro, and your power consumption will probably be in the range of 50 to 60 megawatt. And now you're starting to ask yourself a question. At least I am. Maybe not. Maybe Estonia and Tallinn have so much money they don't care to say, well, or just do it like that. 1.5 billion euro. What is this? This is just every citizen of Estonia paying 1,000 euro, if I got that number correct. 1.5 million people times 1,000 is 1.5 billion. So every one of you paying 1,000 euro, you get the fastest supercomputer in the world. Well, I did not count in the operational costs, so you need to pay another 1,000 euro for that. You're starting to wonder whether this is okay. And is this something which is unusual? The answer is no. We have seen this with most technologies. Yeah? You're pushing the technology to the limit until you get to a point where you're asking yourself, does it make sense? The largest airplanes in the world, currently the largest used airplane in civil aviation is the A380. It's huge. It's fantastic. The problem is just it's not very useful. So people are starting to decommission the A380s. What happened to cars? People of my age know that in the 1970s, when we saw a car, we were trying to find out what the maximum speed is. And car industry was trying to build more horsepower into that. Yeah? 200 PS, 300, 400, 500. And the last one to build one of this stupid system was a German guy. It was Piech, who was running the Volkswagen company, and he said, I want to build a car with more than 1,000 horsepower. And he actually built it, but at that time, everybody had found out, well, you know, cars. How many of you have ever driven a car at a speed of 200 kilometers per hour in Estonia? So in Germany, it's legal, but only if you get up at like 2 o'clock in the night, because then the highway is empty and you can go for like 20 kilometers and try that. But other than that, you go at a speed of, in a city of 30 to 40 and on a highway at a speed of 120, 110, 130, something like that. So why would we invest in cars being faster? Just to say it's faster. And the question is, why are we going to invest into supercomputers just to say it's the fastest system in the world? And now I tell you a secret, small secret. We have this peak performance, the maximum speed. Now in your car, the speedometer says something. Which car do you drive? Hyundai. 240, I guess, is the maximum number on the speedometer. The maximum speed is probably 210. So there is a slight difference, right? Okay, that's normal. That's very normal. And you drive a Porsche, it's 320, but the maximum speed is 285 or something like that. So there is a difference, okay? So when we were talking about these systems, we said, well, okay, there's a maximum speed and we will get to 90% of this. Fair enough. I mean, nobody's perfect. No system is perfect. This one was an old traditional system, 80%. Well, that's good. This one here was more like 15%. Remember 240? 15%? That's 36 kilometers per hour. That's the speed that you get from your car. Would you be disappointed? Probably on the highway. Yeah, you try to accelerate, maximum speed is 36. Yeah? And this one here, that's more like 3%. So we're getting peak performance but we can no longer use it. Anyone have a guess what the problem is with HPC? Remember what I said about the 1,000 people trying to build a house? There's so many components, you can never use them to actually solve a problem. Because you're just replicating. It's 1,000 processors, it's 10,000 processors, it's 100,000 processors. Oh, fantastic, every time I get a factor of 10. But do I get it in the actual, real applications? The answer is, unfortunately, no. Yeah? I'm sorry to be so devastating today. So we have a cost and we have a sustainability problem. A colleague of mine once said, Michael, whenever I see you give a presentation, I think I should send you to a doctor to get some antidepressant treatment. So I'm sorry. I'm the negative guy in the community. Yeah. So let's look at what HPC can do. We are very strong. We are a well-established community. Now in Europe, if you say I'm an HPC expert, European Commission asks you, how much money can I throw at you? Yeah. Just try it. It works. Yeah. So we're well-established. We have a history of disruption. So we moved from this technology to that technology, and now we are moving from CPUs to GPUs. Great, we're used to that. We know how to handle that. We just tell our users, you're stupid using the old technology, you need to learn about the new technology. Users complain, we say, we're sorry for you, but that's the reality. Yeah? We're very good at that. Yeah? And HPC is a key technology in many fields. If you look into biochemistry, medical applications, you're looking at HPC. So this is a strength of HPC. And this is where you have an impact on the world. There is some weakness. Moore's law is going to an end, and the operational costs are exploding. It's getting increasingly more difficult to convince the president of the University of Stuttgart to pay for the supercomputer. Because today I tell him, it's not so bad. It's only like 2% of your budget. Yeah? If we continue like this, next time I'm going to tell him, it's not so bad. It's only 5% of your budget. 5% is a lot. I mean, we have 300 professors and 130 or so departments. So 5% is just cutting 6 departments because we cannot cover the costs anymore for the people. We need to pay for power. Yeah? So that's a weakness. Now, threats. Threats. We may not see further breakthroughs in technology. Yeah? People say we should just try to change technology and everything is going to be better. We have a lack of governance funding. It should say government funding. I'm sorry for this. Everybody correct this in your brain. Yeah? You have this nice device which is called brain. The threat is that we get a lack of government funding. Why do we get a lack of government funding? It's very simple. That's about science. What is a scientist when a scientist talks to a politician? A scientist is a person telling the politician that the future is going to be bright. It's going to be better if we get the funding. Okay? So the story of HPC is, you give me more funding, you will get a much brighter future. Better cars in Stuttgart. Yeah? Or some way to treat cancer in some other place. Yeah? What are we going to tell governments in the future? They tell me, buy a new supercomputer, what can you do with the supercomputer? I will say, well, if you give me twice the money, I can do the same thing I can do today. That's not really encouraging for a politician. They usually don't like these kinds of projects. Yeah? And there might be a lack of interest. Yeah? People saying, it's expensive. Universities deciding to close HPC centers because we don't need that. I know of one university who said, we are a technical university, that's why we don't need supercomputers. It was interesting to hear, but yeah, that's mainly because they say it's too expensive. And if it's too expensive, then we should just give up on it. I mean, if you have this choice of spending 5% of your budget as a university on HPC or on 5 different fields of research, each of them being fancy, popular and everything, what choice are you going to make? Yeah? So we need to keep that in mind. Opportunities. We may see new architectures, neuromorphic computing, trying to build a processor that works like a brain. The main problem of neuromorphic computing is, anyone know how the brain works? Anyone has expertise in brain? Okay, to tell you the truth, nobody knows how the brain works. We know how parts of the brain work, but we don't know how the brain works. So we know how neurons work, but we don't know how to work together. That's a real issue. Anyway, we're trying to build computers based on this. We're trying to build photonic computers and quantum computers. We're trying to work on new methods to better use the systems. And we see AI as a new driver. Now, Fabian, how long have I spoken already?
Around
10 minutes.
10 minutes, yeah. A little bit more, maybe.
Should I skip the philosophical part?
No, the philosophical part is nice. We can handle it.
Okay. Now, when we talk about this simulation, we're talking about trying to describe the world in a way to calculate the future. This is if you ever read Auguste Comte, Positivism. You never read that? No. He literally says the purpose of science is to understand the world to predict the future. That's what we're trying to do in simulation. Now, the idea that we're currently pursuing is this one here. We say, okay, we start with reality. And that's an historical approach, a historical philosophical approach. We start with reality and we try to find what we call a physical model. Now, I call a physical model a model that tells you things like the higher this one is, the faster it gets when it drops. Yeah? That's a physical description, a physical model. It tries to find causality. If I do this, that happens. Yeah? We were able to do this a long time ago, and we started to build mathematical models. Now, you're familiar with mathematics. Come on, even if you're not IT experts, you're familiar with mathematics. But do you know since when we have mathematics? Only since about 800 years. So it's a fairly new science. Architecture is much older, right? No, slightly. So what happened, we had to work on these mathematical models, and actually in the 19th century we had a lot of mathematical models describing physical behavior. Like this one falling down, or that's very interesting if you ever read Greek philosophers. Look at descriptions of what's happening to an arrow that is thrown and how to describe why it has this curve. And they say it falls down because the impulse is not strong enough, and when it runs out of impulse, it sort of falls down. But they had no idea that there is laws of physics like gravity and things like that. But in the 19th century, we had something like this, and we had the mathematical models. And actually, there was a German guy who was giving a talk in 1900 in Paris. In Paris, there was the World Fair, and there were all kinds of congresses, and David Hilbert was giving a presentation on the, I don't remember exactly, 27 problems of mathematics in the 20th century. So it was 1900, so he was talking about the next 100 years. And many of these problems were related to what can I do with these mathematical models. Because the mathematical models, how many of you are in partial differential equations? If you ever heard about partial differential equations, you know that we hate that. Yeah. A partial differential equation is an equation which you cannot solve. It looks nice. It doesn't look that bad. Yeah? So it looks like there should be a solution, but unfortunately there is no solution. And for many of these partial differential equations describing the physics, what we can do is we can give proof that we can solve these equations. But we don't know exactly how to do it, at least not analytically. But then David Hilbert and then many others invented what is called numerics. So you don't calculate the exact solution, but an approximation. Now, Estonia is a very flat country, but maybe you have seen a mountain. How many of you have seen a mountain? In real life, standing in front of the mountain and then figuring, okay, it's going to be steep. Now, if you go up one of the streets in Austria to the mountains, there is a sign saying, it's a triangle, and it shows a black mountain, and it gives you a number, 7%. What that triangle is saying is that the average steepness is 7%. And that's what you're doing with partial differential equations, because partial differential equations have a steepness. Differenzenquotienten. Okay, sorry, that was German. Anyone talking about mathematics knows German. So you just average everything out. That gives you a numerical method, and that's why we have these meshes. You have all seen meshes. When you see on TV anything about supercomputers, you see meshes. Yeah? What happens is that each point, you make an average of the surrounding points. Now you need billions of points, which gives you systems of equations of the size of 100 million, a billion or so. Now how many of you don't have a university degree? Yeah? So but you have a high school degree? So you know how you solve a system of equations, right? Yeah, Gauss elimination, straightforward exercise. 2 equations, 2 unknowns, easy. 3 equations, 3 unknowns, easy. 4 equations, 4 unknowns, high school degree. 5 equations, university degree. Unfortunately, billions of equations take long. How long is long? That's easy to calculate. If you do it the way you learn it at high school, it's what we call n to the power of 5. So for 1,000 equations, you need 1,000 to the power of 5 steps. That gives you the number of floating point operations that you need. So these guys knew exactly how to do it, but they had no machine to do it. And actually there were people who had a job description which was called computer. Computers were humans. Yeah? Computers were people sitting in a room like this at a table, and someone was handing out problems to do multiplication or division or addition or something like that, and then would collect the results. That's how they computed. Supercomputers are much better, so what we got is, we got computers with some hardware architecture. Yeah? People invented the computer. By the way, there were 2 people who invented the computer. One was a guy called Turing, and the other guy was a guy called Zuse. Turing was a British guy, and Zuse was a German guy. One of them invented the computer because he was lazy, and the other one because he was clever. Guess who was who? Yeah? So Turing invented it because he was very clever. He was playing around with this idea of building such a machine, and then later on used it in World War II. And Zuse was an engineer, and he was bored because he would have to do all these calculations. And he decided he should build a machine. So he was lazy, that's why he invented the computer. That's how the computer came into being, and there was some hardware architecture. Now the problem is, you're starting from that hardware architecture, and you need to find a way to program that architecture, and you need to find a way to come up with a program structure. And what we see here is that we are coming from the top, so we are coming from reality, describing it in mathematical terms, coming up with a scheme to solve the problem, and we are coming from hardware architecture, trying to program that, and then trying to bring these things together. That's what I call the simulation gap, and that's what most of the scientists in our fields are working on. It's not so much working on the physical and mathematical models. It's on how the hell do I get these fucking partial differential equations into that supercomputer, which was never built with partial differential equations in mind, but rather with being able to add, multiply, divide. Yeah? A supercomputer is not a system to solve partial differential equations. It's not even a system to solve any kind of mathematical problems. It's a system to do basically 4 things. Add, subtract, divide, multiply. Period. Not more than that. Yeah? And this is a hell of a job here. And those of you who are running a supercomputer and trying to support the users know exactly what I'm talking about. Because the application people come and they say, you know, I have this fantastic scheme and I have this new concept and blah, blah, blah. Now, could you just write a program because you have this supercomputer and they pay you for having the supercomputer and you're supposed to do the service and here is my garbage mathematical collection. Please turn it into a program.
And if you have 2 computers, then you can do it twice as fast.
Yes, right. Yeah. People coming to us and saying, it runs on my laptop, so please run it on 5,000 nodes. Yeah? And that's the problem here. That's the problem here. And the reason is because we started with this from a philosophical and physical point of view. Yeah? You read Aristotle, you know what I'm talking about. Huh? And here you're starting from a purely technical machine. And you try to bring this together. Now what I'm recommending is to do something completely different. Recommendation. Hey, where are we? I'm ahead of my time. Hardware architecture. Think about a programming model. Think about a program structure. Think about a numerical scheme that fits your program. Say, this is what my architecture can do. So this is the best method to use the architecture. And then say, if this is the best method, then this is my mathematical model. And if this is my mathematical model, this is my physical model. But then you end up with this here, what I call the reality gap. Huh? People shy away from doing this because they say, in the end, I end up with something which is nice and fancy and just running fast, but has nothing to do with reality. Yeah? Now, the problem is not to say, okay, it's impossible. The problem here is it doable? How many of you are in fluid dynamics? At least one. Great. So one of you will understand what I'm talking about. In computational fluid dynamics, there is mainly two equations, Euler and Navier-Stokes. Yeah? Euler is simpler, Navier-Stokes is more complex. I once heard a sentence when one gave a presentation of Navier-Stokes and he said, real man, two Navier-Stokes equations. That was a long time ago. I mean, we are talking gender here. Real man, come on. The Navier-Stokes equations were designed 170 years ago or so. Why are we still using them? The reason why we are using them is because we have them. The reason why we're still using them is because thousands of scientists were working on finding a solution to them. Yeah? If you don't want to innovate, you just use that equation, you just use one of the established methods and you incrementally change something. And you get a PhD. That's great. We all get PhDs. Yeah? It's fantastic. You just write a book and find a nice guy and you get a PhD. Yeah? If you do the same thing and say, I ignore 170 years of scientific history, let me rethink, you run into problems. You probably don't find a PhD advisor. Because nobody dares to say Navier-Stokes is stupid. It's the established method. Yeah? It's like the idea of ether. Anyone familiar with the idea of ether? Yeah? There was this idea that the whole space outside the Earth is filled with ether. And that was the established method of describing this. Yeah? Nobody dared to object to that until they found, oh, there is nothing, there is no ether. Yeah? Okay? So it's difficult. It's really difficult, but I think it's worth it because with the old approach, where we were trying to squeeze our old mathematical methods in a new system, we kept losing performance. 3% of a supercomputer. Yeah, we're spending on our next supercomputer, we're spending 100 million euro, and what we get is 3%. It's entirely unacceptable, actually. Yeah. Okay, so it would be worth doing that. And I skipped the next slide because this one is for the mathematicians. It says, this is Moore's law, but this is what the mathematicians did. Remember I said the Gauss elimination method for solving a system of equations for the high school exam, yeah, takes a lot of time. So mathematicians thought about it and they found better solution, actually increasing the speed of such a calculation also by a factor of 10 to the power of 7. That's not bad. I mean, okay. So we are a bit at a dead end with this whole thing of HPC and simulation. Our old equations, partial differential equations, are nice. They are more or less correct. We get some good results. We get faster systems, but actually we cannot use the faster systems. And when we solve the equations, we don't get much better solutions. And actually they only give us like 1, 2, 3, 4, 5% of this peak performance. So there is a new kid on the block, and it's AI. How many of you are familiar with AI? Come to me afterwards. The problem with AI is that it's not I. It's A. That's okay. But there is not much I in the AI. But it's fancy. It's really fancy. I mean, I was talking about politicians before, right? Now show a politician ChatGPT. Let the politician write a question and receive an answer, which is close to the truth somehow. Yeah? These people are excited. Actually, some politicians said we don't need teachers anymore because you can just ask ChatGPT. The point with ChatGPT, just to give you an example, is when you ask who is Michael Resch, which I did a year ago, you get an interesting answer. I was born in 1953 in Germany, and I studied physics in Würzburg, and then became the director of HLRS. The truth is I was born in 1964 in Graz in Austria, which is not in Germany, and I never studied physics, but I studied mathematics. Yeah? What AI does is it just fills the gaps with something that is logic. Now, until about 2 years ago, people would say AI doesn't work. Now they have found a better way to describe it. They call it hallucination. Now you have a technical term. So you can scientifically now work on the hallucinations. That's a fantastic twist. I mean, how many architects are in the world who could say, my house collapsed, so that was some kind of scientifically interesting thing, so let's explore that. Wouldn't you say, well, houses are not there to collapse? So why do we accept it in artificial intelligence that we say, okay, there are hallucinations? It's just wrong results. I'm sorry. It's wrong results. Yeah. So I'm a bit skeptical about artificial intelligence, but there are many ways to use artificial intelligence. They can help you especially, and actually it's not much about intelligence, it's more about analyzing data. They can help you to analyze huge amounts of data and try to find patterns. And if these patterns make sense, you can make use of that. How many of you have heard lectures about statistics? So you know about, now is this international, the stork and the babies?
I don't know.
Who is in charge of bringing the babies in Estonia? Is it the stork?
Yeah.
The stork, okay, okay. So there is statistical evidence that the stork is actually bringing the babies. Because if you have less storks, you have less babies. And what we call this is there is a correlation. And AI is very good at finding out these correlations. And we all know that the stork is not bringing the babies. If you still think the stork is bringing the babies, talk to me afterwards. Okay? What we see there is a difference between correlation and causality. Yeah? Causality causes correlation, but correlation does not cause causality. AI is about correlation. It's not about causality. And that's the weak point of AI. That's what we're worried about. That's where we say if some insurance company using AI to analyze data and then use correlation as causality and change the behavior towards the customers, we don't like that. Any government looking into personal data, using this data to analyze for correlation and then turning this into causality, we are worried about that. Okay? That's the problem with AI. But AI can be a strong tool, and a lot of people are funding AI. The EU has an AI Act and AI regulations, and it also tries to extend HPC systems across Europe to be able to support artificial intelligence. They are also going to pay for training services and things like that. The US has a president, so they have an executive order on safe, secure, and trustworthy development and use of artificial intelligence, Executive Order 14,110. So you see the governments are trying to sort of find a way to control it. Yeah? And when you look at these regulations, what you find is that they are not going to control anything. Yeah? Because it's getting difficult to control this, mainly because AI is using supercomputers. Now, many of these regulations are calling for things to be replicated, analyzed. Now, when I'm using a system with a peak speed of 1 exaflop, that's 10 times and 10 to the power of 18 operations per second. If I'm using such a system to analyze data Who of you can replicate this? 10 to the power of 18 operations per second. You can't. You can use a second system and try to find out whether the second system gives you the same result. But you can never understand what's going to happen. You can never see that. Not even if you see the algorithm. Because the methods of AI are basically what we call machine learning. And the idea of machine learning is training. And you don't get to see what the system actually is learning if you see the code. Just give you a simple example. You have heard about fishes, right? You're living close to the sea, so you know what a fish is. So you're training a system to be able to distinguish fishes of different types. So you're holding a fish like this to a camera, take a picture, and tell the system which type of fish it was. You do this, I don't know how many thousand times, system starts to learn about that fish. Okay? Got the point? Yeah, are you still with me? Please nod. Thank you. Now they did that, and then they checked whether the AI actually had learned what to do, and the AI was not so bad, but somehow the results were, yeah, somehow strange. So what they figured was, they started to analyze it, and what they figured was, there is small fish and big fish. And if you hold a small fish, then the camera will see your thumb. And if you hold a big fish, the camera will not see your thumb. So what the system learned was, thumb, small fish, no thumb, big fish. That's not so useful if you have the fishes coming on a conveyor belt and the AI trying to analyze it, okay? So we really don't see what AI is learning. And even if you say, like these regulations say, you must not have a bias. Like in the US, they say you have to be careful about races. In the US, they actually call it races. Yeah, I hate it because the term does not even exist scientifically. There is no human races. If you never heard about that, there is no human races, okay? From a genetic point of view, there is no human races, okay? Thank you. But they call it races. So they say, take care that this percentage of people in the US is black or brown or yellow, whatever they call it. I think it's Asian, no, it's Caucasian and Asian and African and things like that. When I worked for the University of Houston, I was looking at this and said, I mean, I have no race. What am I supposed to tick here? And they told me, don't make it complicated. So I'm Caucasian, okay? Keep that in mind, I'm Caucasian, white Caucasian. So you can have these kinds of regulations. Obvious biases, you can try to avoid, yeah? But there is the thumb. You don't even think about it. And what is the thumb if you're analyzing medical data of people you have insured? What kind of bias goes into that, which you don't see? Yeah? And what kind of data do we have if we use AI? Anyone ever heard how many female patients are typically used in medical evaluations? Very few. Not to say none. Because most of these medical investigations are using male patients for standardization purpose. We always used male patients, so if you compare something, then we still have to use only male patients. Now, would anyone agree with me that male and female are medically slightly different? So that's a bias that is so natural for the medical research, they don't even see it. Yeah? And the question is, how many of these biases are there that are not seen? Yeah? Even if you have an executive order, I love that term, yeah, executive order. Yeah? And the UK is spending a hell of a lot of money, and South Korea is spending a hell of a lot of money. And they have to correct this for the UK, because yesterday I heard that the government just decided to cut everything. They have to cut their budget, so yeah. So we see a lot of AI centers also in Germany. But now for something positive, I have to say something positive in my presentation. How many minutes still left? It's 4:07 on my watch. Okay, okay.
It's kind of,
Yeah.
your watch is kind of
When is our dinner?
It's
At 7, and we are like Eastern Europe time. Okay. So there is one positive thing to say here, and I would like to point you to that to try to understand how HPC, not in terms of let's increase peak performance much more, and how AI, not in terms of playing fancy games with politicians and showing them something like ChatGPT, how they can actually help us to find better solution for human beings. And I call this concept digital convergence. And what I'm saying here is we don't need that much performance. Yes, we need it in science, we need to achieve breakthroughs and everything, but look at this system here. Yeah, this one is a supercomputer. Yeah, the Prime Minister of the state of Baden-Württemberg bought this one in the year 1986. And he bought it to design German nuclear power plants. And he bought it to do crash simulations for cars. And he bought it to do weather simulations and climate research simulations. So this one here is a supercomputer. Now, I don't know how to program this because there is no compiler. Yeah? But we have the compute power. Each of you has the compute power of a supercomputer in your pocket. So we have enough performance. We have high performance computing everywhere. This laptop here is probably more like 1993. Yeah? Supercomputers which were designing atomic weapons, submarines, airplanes. So this one here was classified in 1996. Yeah? We were not supposed to send one of these systems to any of the embargoed countries. Yeah? Now we just have it. You want to move this to North Korea? It's not so difficult. Take it with you, travel to North Korea, hand it over. I mean, they don't need you. Just buy it in China. Maybe they do a short trip to Beijing and buy a truckload of these here. Even if North Korea wants to build a supercomputer, it's a straightforward thing. Because the power is everywhere. The compute power is everywhere. So we have HPC as much as we need. What we also have is a huge amount of data. Yeah? We do have a huge amount of data. We have a huge amount of data because we started digitalization in the 1970s. A lot of systems are digital. Banks, insurances, government agencies. Well, in Estonia, perfect. In Germany, not so perfect, but we have a lot of information. And then we have everything that, how many of you have a social media account? Dare to raise your hand. I have one. I have one on Facebook. Know why? Because one of my kids was on Facebook and she didn't know it. So I decided to design a supervisory Facebook account. And I gave it the name of my grandmother and also the birth date of my grandmother. They never canceled that account. It still exists. They tend to believe that the 117-year-old lady is having a Facebook account. But I can check from time to time. And now it's no longer a problem, but I still have kids in 7 and 9 years old now. So I do these accounts to just monitor what's happening. Because anyone can create an account. I can create a Fabian Demski account on any social media and then post things like I hate all the social democrats or whatever you want. Okay? Now through the social media we have a huge amount of data. We have pictures, private data, a hell lot of data. We have all this data, yeah? And they are, interestingly, they are sort of protected but public. Yeah? They're protected in the sense that these social media companies don't want to give it to any researchers. Because they say they belong to us, you have to pay for it. Yeah? But when they are accused of collecting data, they say, no, 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 they belong to the users. It's not our data. We don't collect data, it's your data. Yeah, it's your data. It doesn't belong to us. You cannot charge us for collecting data. That's an interesting thing. I spoke to German lawyers and I said, what are you doing here? I don't know Estonia, but is it legal if you take pictures of your neighbor? If you install a camera? or a microphone in the house of your neighbor? Is it legal?
Camera on. No.
Well, I would say no. I mean, usually a country has a regulation saying that you must not spy on your neighbors. Most countries even say that the government must not spy on the citizens. Okay, you're selling Alexa, you're just collecting all this data. Huh? It's weird. It's weird. And lawyers start to understand that. But anyway, we have this data. Now, we have artificial intelligence methods. Now, ignore the intelligence and think about the data. AI basically is a technology to analyze data. Yeah? We have these methods. What is missing, in Estonia, I don't think it's missing, but in Germany it's missing, is this one. People. Yeah? We don't have enough people in Germany to understand these technologies, data, AI, high-performance computing. The interesting thing is we don't even have IT education in our middle and high schools. We recently started a campaign to convince the state of Baden-Württemberg to do more than 1 year of computer science education. Because the 1 year of computer science education, what is it that the people learn in middle school in 1 year of computer science? Start your computer, start the browser, type in a URL, and see what's happening. Another year is over. Okay? We're trying to push them to do something because Germany is a black hole. Yeah, when you look at all the European countries, there is a map. The European Commission gives an IT report, and it also talks about education. And then you see which country is doing how much, and middle school and high school. You see all the nice colors, each of the countries being yellow, dark yellow, light yellow, whatsoever. In the middle, you see Germany, it's black. No education. Yeah. So we have this problem, you don't have it. Now I would like to emphasize the issue of data. Now data, people are worried about data, and one of my students was doing a PhD, and I find that one interesting because what he said is, we have several issues here. Yeah? We have the organizational issues, we have the technical issues, and the legal issues. Now people are mostly talking about technology. How many disks do I need? How many tapes do I need? How do I organize? This is what the computer centers do. Yeah. We take care of this and we say, it works. Legal people look into this and say, there is some copyright, there is some privacy and so on, what shall we do? But then there is some organizational issues there. You do have all these data. A company like Mercedes has a huge amount of data. The point is they don't know which data they have. Yeah? So the challenge is not so much to have the data, the challenge is to handle the data, structure the data, understand which data belongs to which, say, physical world or human being or whatsoever. And then there is something else which I would like to show you, and I like this one very much. That's a slide showing what happens to data, and that's according to Michener, William Michener, already in 1997, and I love it. He was talking about scientific data, but it's the same for other data. At the beginning, you have all the data, and then you start to lose details, and then someone retires, and you start to lose more information, and then the guy dies, and then in the end, you don't know exactly what's happening. Does this happen to you? The answer is yes, all the time. All the time. And I'll show you another slide, which I like very much. We were talking about what we called dark data. Yeah, we were trying to categorize our own data. At the time, that was 2020, we had something like 20 petabyte. That's not much. Yeah, we're trying to categorize. And we said we have 3 categories. One is, we know who the owner of the data is, and we know what the data is about. The second one is we know the owner, but nobody knows what the data are about. And the third one is we don't know the owner, and we don't know what the data are about. Now you would say we just throw it away, but you can't throw it away because you don't know what it is. And there are some legal regulations. If you do a PhD, you have to keep your data for, I think it's 10 years in Germany. Yeah? So I need to keep data, at least for 10 years, even though I don't know what these data are. And what we saw then already in 2020 is that the amount of dark data is increasing. What's behind this? It's exactly the curve that we saw before. Someone is leaving the company. In a university, who is leaving the company? The PhD candidates. Who does the research? The PhD candidates. So the PhD candidates are the ones creating the data, but they are the ones leaving the organization. So what we see here is PhD research. These are PhDs leaving and nobody taking care of it. And then there is another phenomenon which is, I don't know whether it's only in Germany, but maybe other countries handle this in a much better way. In Germany, a professor is a god. And there's a joke. What's the difference between a German professor and God? God knows that he is not a professor. What that means is, as a professor, you're running your department. And you're running that department the way you want to run it. And when you retire, you take care of most people in the department. So you make sure that this guy finds a position there and that guy finds a position there. And when a new professor comes in after 2 years or so, what he finds is the secretary waiting for him to build up everything from scratch. Sometimes there is this old guy who said, I'm only 3 years away from retirement. I'm not going to leave just because a new professor is coming. But that's it. When I came to my department, there was the secretary, and there were 2 guys in their late 50s. Yeah? So basically, you're starting from scratch. But what that means is, this one is increasing also when a professor leaves. Yeah? Because the new professor doesn't know anything. Yeah? And there is no legal regulation for documentation. Yeah? So that's one of the problems of data. Not so much do we have the data, but much more, what is the content we're talking about here? Yeah? Like in our case, is this a flow simulation or a structural mechanics simulation? If it's a flow simulation, what was it? Was it an airplane, a helicopter? Yeah? You may guess this one was created using this account. 20 years ago, this account was hydraulic machinery, so it might be a turbine simulation. You can never reconstruct it. You cannot look at the data and say, this looks like U, V, W. So it should be flow simulation, 3 directions of speed. And there is some P, so it's pressure, so it must be some kind of flow simulation. You cannot do that because what you get is a file that starts with numbers and ends with numbers. And that's, first of all, stupid. It's really stupid. Because what you're doing is you're using these supercomputers to create data, and then you're writing your paper, and then basically you throw away the results, which is plain stupid. Because you could use AI to analyze all your simulations and then tell the new PhD candidate, we have done this before, and we have seen this. And if you want to try a new method, I can tell you that this and this and this worked and this did not work. So what you have to do with your data is you have to have a curator for your data. There has to be a person who knows. There has to be a system that describes. Now, the most primitive form of doing this is what we call metadata, a description of your file. And a very simple way is blood flow, carotis, 1988, RE20. That told you that I did a blood flow simulation in the carotid artery of the human being using a Reynolds number of 20. And I did it in that year. That's the most primitive method of having some kind of metadata which tells you what is this file about. Yeah? But you need much more than that. And you need to understand what's in your data. And that's what is tricky. Because people don't care about data. Sometimes they don't even know that they create data that have some value. Yeah? But I promised to say something about what we can do with data. And this is my favorite example. So I said that I'm going to talk about a problem which some of you have heard about. Has any one of you heard about Corona? Great, thank you. Yeah. When Corona came to Germany, it was first not a problem. Yeah, it showed up in Wuhan, and then politicians said, no problem, it will never come to Germany. And even if it comes to Germany, we are prepared. Yeah. It's always bad to make jokes about politicians. But okay, it so happened. So I think it was in March or early in April when they said, okay, that's a pandemic, we will shut down everything. And on a Friday night, I got a phone call from one of my head of departments. They never call me, they sent me email at midnight, and I'll just reply. But he called me, Ralf Schneider. So I picked up the phone, it must have been something important. He told me, yes, these guys here, the Federal Institute for Population Research, want to talk to me. Okay. So he said, I'll call them and tell them your phone number and they can call you. So we had a phone call, and the problem was they were working on models to describe a pandemic. They were using this model and they were running it on a laptop. And so they were able to simulate 1,000 people. 1,000 people is not a lot if you try to simulate a pandemic, right? By definition, a pandemic is a pandemic, not a village-demic. It's more a pandemic. Yeah? But yes, we worked together with them, and we set up a system to predict the intensive care unit usage. Intensive care units was, at least in Germany, the most critical thing. Yeah? If people get sick, that's okay. The problem is if they need intensive care unit treatment, because if there is not enough intensive care units, they are going to die. And that's what we saw in Italy, which was it? Bergamo. We saw it in Strasbourg, we saw it in New York. Okay? We probably didn't see it in some other places in the world which are not so popular or not that visible. Yeah? So that was the idea. Predict what's going to happen to the intensive care units. And now what happened was you have the Robert Koch Institute, which is in charge of analyzing and sort of monitoring what's happening. And they had all the data. And now we could use this data, analyze the data, use the results of that analysis to simulate what's going to happen. Feed this back, and then the Bundesinstitut, the Federal Institute for Population Research, would send it to the Ministry of Health and the Ministry of the Interior, would take measures. Now Germany is a federal country, so we have these 16 states. So we did a prediction for each of the 16 states. Now the bad thing about these issues is that if you simulate something like this and you try to validate your simulation, it's practically impossible. Why?
People have to die.
No, because people react.
No. Okay.
It's like you're speeding and there is a wall in front of you and you say, I predict that you're going to die, but you don't die because there are the brakes and you use them. And that's what was happening. Politicians were looking at the numbers and said, okay, we need to do something about that. So we were practically not able to validate what's going to happen, but there was one guy in Thuringia, small state in the east of Germany, and he did not use these numbers. And the fortunate thing is that he gave an interview to one of the most important newspapers in Germany, the Zeit, and said, we did not believe in the numbers of the scientists. We had all the numbers, but we did not believe the numbers. What happened was that they were running out of ICUs. And the German army had to fly out patients to other states of Germany to save their lives. So what we figured was, because this guy here just decided to ignore the prediction, what we figured was that these predictions were roughly correct. Yeah? The problem with this is what I told you right at the beginning. You're talking to society, you're talking to politics. That's one of the discussions that we have in Germany. Our predictions were sort of never right. And you can always check that because we publish these results, all the scientists publish their results, and the general audience can look into this and can say, okay, look, in June 2020, there were some scientists who predicted that this and this is going to happen, but it never happened. Well, if you take measures to avoid it, certainly not going to happen. And this communication of telling people there is a danger, if you react to the danger, you lower the risk, that's important for us. Yeah? And that's important for politicians to understand that if we give you information, if we give you simulated results, there is a certain probability and you have to make a political decision. Now, I would never recommend that any politician make a decision just based on simulation results. Because what is the weak point of this here? What is the really weak point of doing any prediction of pandemics? Anyone have an idea of what the weak point of this is? Anyone ever heard about a physics law describing human behavior? There is none. Human beings are bound by the laws of physics. Yes, okay, we cannot fly. Yeah, okay. But our behavior, like me shaking hands with you or not, is unpredictable. And shaking hands is important in a pandemic. You don't shake hands, you reduce the risk of an infection. So when you go into these types of simulations, now you're not talking equations from the 19th century, which were proven in experiments over and over and over again. You're trying to describe something where there are no laws of physics. You're trying to describe things by making assumptions about human beings. I'll give you an example where it did not work out. You may not have heard about it. The event is called the Love Parade. Anyone heard about the Love Parade? Yeah. There was a Love Parade in Duisburg. And the idea was we have this area, and it's about 2 kilometers long, and it's 200, 300 meters wide. And we try to find out what the maximum capacity is. A lot of people go there, enjoy themselves. So they ask a colleague of mine to do a simulation. Now, such a simulation is you have each person is an agent. You describe the agent, you describe the interaction of the agents, and then you let the system run. Assumption being that you enter the area here, and then people move through the area and leave it here. The simulation showed that I think 150,000 or 200,000 people should be okay. And then something happened which was not expected. A group of 10, 15 young people, my size but much younger and stronger than mine, entered that event and immediately figured the Love Parade. We thought that would be something different. And so they decided not to move to the end of this area, but to turn around. So there's only one expert in computational fluid dynamics. What happens if you have a flow of particles going that direction and you have 10, 15 particles turning around? What happens? Anyone has any clue? You create turbulence. And they created turbulence. And the bad thing was, at the point where they decided to turn around, the area was going like this because they had to go under a street. So there was a narrow tunnel, and they were trying to push against the flow of other people in that narrow tunnel. What happens if things like that happen is?
Pressure builds up.
Pressure builds up. How do you react as a human being?
Panicking.
The point was people panicked. How do people behave when they panic? Anyone know how people behave when they panic? Nobody knows that. People are entirely irrational. People kill their own children when they are panicking. They stomp on their heads to protect themselves. I don't know how many people died, 15 or something like that. They charged the guy who did the simulation. And they said, you did a simulation and you predicted that there is no danger. People will flow smoothly from left to right. So they charged him. And he was able to get away with this by saying, wait a moment, what I did is I said, if people enter here, and if they move this direction and exit here, then the whole situation is safe. So when we deal with human beings, the problem is that we don't know what's going to happen. And artificial intelligence cannot solve that problem. Simulation cannot solve that problem. So when we're talking human beings, we should not do any of this here. Yeah? There is another example which I like very much. It's from Uwe Wössner. When you put together data and information about a city, this is Stuttgart, you can do all kinds of simulations. And now you can play around with these things, and what you can do is you can do all kinds of city planning, you can do transportation planning, you can do that interactively, integrating people with their cell phones with an app where they can give you feedback on how they feel in this or that area. And what you can do is, if you do traffic information, you can remove buildings or add buildings, you can remove streets or add streets, you can close streets, you can turn streets around and say it was unidirectional this way, I'll turn it around the other way. So what this can do, if you have enough compute power, if you have all the data, and if you have AI methods to analyze the data, you can actually interactively do city planning. And that's very useful. What this doesn't solve is the problem of integrating people, and it doesn't solve the problem of designing a public space where people feel well. Because again, this is nothing you can simulate. You cannot say, I have a model of the human being, and if it looks at a facade and the facade looks like this, then the person feels well, and if it looks in a different way, it looks bad. What you can do is you can do the technical part of the planning, and you can try to get the feedback from the people and use it. Yeah? But that's a mighty tool, because it allows you to create something which we tend to call a smart city. And so what we're currently trying to do is to create a full digital twin of the city of Stuttgart and then the region of Stuttgart. And the data are there, and they are, surprisingly, they are public. Yeah? So we can get access to the data, we can integrate these data, and the next step is then really to, over time, step by step, traffic data, and we recently found out that you even can get hold of data about salaries, income of the people, and you can then play around with that, and you can work with that. Okay, so what I was trying to do is, I was trying to show you that HPC has reached a point with an impressive performance that can help you solve all the problems that you can solve using mathematics. I showed you that we are getting to the point where we will probably not see further improvement in hardware, which leaves us with the message that we should work on the software, on the solutions. Rather than getting 3% of the system, we should get something like 50%. We should probably not focus so much on what the theoretical peak performance is, but rather on how we can best use the system to solve the problems that are real. And what I also tried to give you is that we are not talking purely scientific or technical questions here. We are talking about a methodology that helps you tackle general problems that are not only interesting for the scientist publishing a paper, they are interesting for society as a whole and for politics as a whole. So if you take these things and you put them together, you can start to analyze problems that have a technical side to it, but that have a human relevance to it. Yeah? And that's something we look forward to do with you, and that's why I'm happy that we signed the collaboration agreement, because I see that you're working, when I look at the pictures in the back, for example, you're working in fields where we currently have some expertise in telling you what technically is going to happen, but you have the expertise in how I design things, how I shape things, yeah? And how I work with things that we are currently not thinking about. Like one of the things I'm interested in is how do you design a city that is resilient in terms of climate change? Yeah? When I was a kid, I knew exactly which path to take not to be exposed to the sun. I hate the sun since I was born, I'm sorry. Yeah? Yeah? So how do you create a city if you have more exposure to sun, higher temperatures? How do you create a city where you still can live? And that's not a fancy problem for someone who is just exotic. That's one of the key problems of the future. Because what we're going to see in the cities is people are going to die. Yeah? We don't have it on our screen. We're starting to analyze these data, but estimates are that in a country like France, we're talking about 10,000s of people dying within 2 weeks or 3 weeks because of the heat, exposure to the heat. And we're going, well, you're not going to see this because you're a cold area, yeah. But Stuttgart is going to see this. And when you look into the city planning, you see that you have to bring in geography. Yeah? You cannot say Stuttgart is flat. Yeah? What happens in Stuttgart is that you have areas that are like 5 to 7 degrees hotter than the rest of the city because of the geographic location. You add to this that everything is concrete, no shade, no nothing, you increase the temperature by another 5 degrees or so. So officially the weather report would say 32, but you got 42 there. Yeah? That's not so nice. Okay? With that, I'd like to thank you for your patience, especially listening to my stories. And if there are any questions, feel free to ask, because we still have something like 1 hour or 2 hours, or well, it's a 5:38. We have like 1 hour and 40 minutes for questions if you want. And there were a lot of people who said they know something, and I said, talk to me afterwards. Okay, if you have any questions, just feel free to ask. Thank you.
Just a quick one.
Yeah.
What about quantum computing?
Yeah, good question. Good question. It's the standard question. Yeah. It always comes up, and until about 4 years ago, I said, quantum computing will be there in 10 years. And then I said, this is what I have said for the last 20 years. Now I'm saying quantum computing will be there in 10 years, and I believe this time I don't have to modify my statement. What we see is that the technology is sort of forking out. So people are trying different ways of doing quantum computing. There is like 6 different European approaches to do quantum computing, technical approaches, and we see more of them. And what is happening here is that people start to understand that there is the potential to solve new types of problems with quantum computing much faster. So they're trying to explore what is the perfect technology to do this, both in terms of technical, but also in terms of economical. So we have reached a situation that we had in the IT industry back in the 1950s, 1960s. And from there, I believe that we will see some kind of competition, which will mainly be driven by the economic part. How much performance can you get for how much money? And then we will focus on maybe 1 or 2 technologies. I don't expect to see 7 different technologies surviving. Maybe it's 2, maybe it's 3. And once we settle with these 2 or 3 technologies, the competition is for optimization to get the better performance for the same price, comparable to what we saw with Moore's Law. And that's why I think that when I retire, which is officially on the 1st of April 2032, I'm an employee of the state of Baden-Württemberg, so I know exactly when I will retire. By that time, no, because I'm getting 60 and they won't change it for people older than 50 or something like that. Yeah, that's what they did last time. They said, okay, we change it from 65 to 67, but not for people who are older than, so they will not change it for me, which is good or bad, I don't know. But by the time we will probably have procured a system and decided to install it, but I think that by, say, mid of the 2030s, we will see very productive quantum computing systems. It will be probably later at HLRS, because when you go into the basic research science, physics, chemistry, people are more happy to play with something which is entirely new. While the engineering people say, I need a solution that actually works, so we are going to be latecomers. We might see such systems 2030, 31, 32 in other centers, which are more focused on the basic research approaches. Does that answer your question satisfactorily? I mean, it answers your question, but are you happy? It's okay. Okay, thank you.
Say what it changes.
Well, it will. There are currently 2 theories, or two ideas what's going to happen. Some say if we combine the traditional IT approach, HPC approach with the quantum, then we can use part of our problem, put it on the quantum computer, speed it up by that, so we can speed up the overall system. Others say no, we will probably say that the traditional problems, like Navier-Stokes equations, okay, there is 1 exaflop, you can work with that, that's good enough. while new problems will move to quantum computing because quantum computing will drive the development of these new problems, just like the computer helped to drive this mesh-driven approaches. Yeah? In mathematics, you have different approaches, but some of them better fit on the traditional computer, so those were the ones that people were following up. And some say that quantum computing might create something like this. And then we will probably all work more on traveling salesman problems and other kinds of optimization problems, which when I was a student were said to be NP hard and therefore couldn't be solved. But these problems might be then more in the focus of our simulation and of our research. Yeah? I tend to side with the second approach, saying we're going to see a whole new world of algorithms that will help us solve new problems. Now, even more happy? Okay, thank you. Further questions? With my students, I don't leave the room without 3 questions. So that was 1. Yeah, thank you.
Where you had the physics gap instead of what was the other gap?
One was what I called the simulation gap,
Yeah.
where we start with physics, mathematics, numerical methods, and then all of a sudden realize that it doesn't work on a computer. And the other one I called the reality gap. Yeah, where I said we start with the hardware and just say what does it need to be very perfect on this hardware, and then we come up with a model that is perfect on the system but probably doesn't fit reality. Yeah.
So the question was, would the second version that you were saying, could that serve as a bias control against a humanity understood world? Because you're starting from the machine. I don't know if
Yeah.
I
I think I understood your question.
So like all of the ways that we have ended up describing things,
Yeah.
reality, what you said,
Yep.
are starting from our own concepts and words, that is the cup and this.
Yep.
Could we just start experimentally running backwards things to see how reality would like
5 years ago, I would have said yes. It helps us to get sort of rid of that bias that we have. But now I tend to believe that the computer in itself is a biased machine. It was created to sort of follow this traditional approach, pushing the limits of this traditional approach. And when we start with this hardware again, trying to sort of get around the old bias of physics, mathematics, numerical methods, it won't work because the bias is already in the hardware that we're using. So I'm not sure. I'm currently thinking that we should probably try to do both at the same time. Come from reality, try to go to a machine that could help us, and start from the machine that we have and go up, and probably then we can, yeah, to some extent, not get rid of the bias, but get a better solution. Yeah? I'm currently, from a philosophical point of view, I think that the computer, how do I say this without losing all the funding from all the agencies?
No, well, they are not probably here.
I think the computer is a dead end. I think it's a dead end. Because what it basically does, it sort of inflates the bias that helped us to come up with these mathematical solutions. It's so strong, the machine is so strong that nobody dares to think in other terms than these very rational mathematical terms. And that is also my concern about AI. I talk to lawyers, and they're very excited about it. And they say, I can save a lot of time on this and this and this. The AI could just read all the court rulings, and then from the court rulings find out about the rules, and then I just tell the machine I have this case and what is the court going to rule. Just give me the answer, and then I know I should go to court or not to court. And I keep telling them that the bias of the machine is the assumption that everything is logic. Okay? And that everything can be expressed in some kind of mathematical, logical term. But when you look at the legal system, what you see is, I need a legal expert here. Does anyone know what the court proceeding is called? Bei uns wird es Verhandlung genannt. Do you know what it's called? In English, yeah. It's the trial, but within the trial, And that's best seen when you look at a US trial, because they are very public and they very much emphasize the exchange between the accuser and the defender. What this trial is not about logic. It's not about looking at the rules and then using the rules to come to a verdict. It's a negotiation of people who say, you broke the law, so you should be held accountable, and a person saying, no, I did not break the law because I did not have the intention or I wasn't there. It's a dialogue and it's a negotiation. And the result of such a trial is not a logical conclusion. The result of this trial is a decision by a person who is empowered by society to make a decision to sort of repair the damage that was potentially done to society. So the legal system is not about 2 + 2 = 4. The decision of a court is more about you shouldn't have done this, or it was so bad you should be punished, or no, it's okay. Yeah? It is negotiation. And a computer is not about negotiation. A computer is about calculation. And these are two very, very, very different things. Now that's one of my concerns about AI is this, that people say, now I can step back, and it's even more fair because it's a computer system. It always comes to the same conclusion, whether it's Donald Trump or you, it always comes to the same conclusion because it applies the same rules. Yeah? In that sense, yes, the legal system tries to be fair and tries to avoid this human bias. But by avoiding the human bias, it takes completely out what the legal system is about. And there are many other systems, like medical treatment. We tend to think that I have this type of cancer, so the doctor says, okay, you need this kind of treatment, and that's it. When we're talking about a human being, we are talking about the situation of that human being. So a doctor looking into this can never say, I'll treat this patient exactly like I treat that patient, because the patients are different. Now, let's exclude male and female. Yeah, we're treating females on procedures that we tested on males. Funny thing, but yeah, okay. But there is a social environment to that patient. Now, when I break my leg, you don't worry too much about the social environment, but when I take treatment for cancer, and I look into the methods that I have to look at what the patient is in the social environment. Is there someone there to support the patient when the patient feels bad? If so, if there is a number of people, if so, I can do this chemotherapy and everything. People definitely feel bad in chemotherapy. It's not fun, and it's for weeks and months. And you need a stable environment to carry you through. You do that same with a patient with no relatives, no nothing. Patient will go away after a few days. I saw this when my kids were in kindergarten that was connected, sorry, I'm telling stories. I was connected to what is it called, a home for the older ones. So the kids were talking to the old people there. And after a while I realized that some of the old people were going away. So I spoke to the people who were working there, and they said, well, that's something which we know. Old person come in, no relatives, no visit, dies within 3 months. Old person comes in, relatives, visits, person lives for 2, 3, 4, 5 years. Yeah? Now that's nothing that you can put into an algorithm. And as a doctor, it's nothing that you can put into an artificial intelligence system. Yeah? But you need to consider that. You need to think about that. And there are many systems that can be described digitally, but don't cover everything. And the question is, what do you lose when you bring in AI to replace this human decision? I don't know what your question was, but it was a nice exchange. Thank you very much. There was this third question I was asking for.
I can ask.
Yeah, thank you.
So in the beginning of the presentation, you were mentioning 2 types of computers.
Yeah.
One is like the classical one, that whatever the HPC is.
Yeah.
Then quantum computers.
Yeah.
And
Yeah.
then there was one which made me curious, was about like replicating the brain.
Yeah, the neuromorphic.
Exactly.
Yeah.
So usually, what I have heard always is that they try to, at least at some point, they try to make algorithms replicate the structure of the brain. But this is like, so I'm not an expert, so this is the first time for me. So how far is the development of these types of computers and where they are actually used at the moment?
I'm not an expert for this field.
Okay.
I recently spoke to a research institute in China about that, and they said we are all at the beginning. There is two ideas. One is to build sort of a software, an algorithm that sort of replicates the behavior of the human brain and run it on a traditional computer. And the other was also in the Human Brain Project in Europe, to try to use the knowledge that we have about the brain to design a computer that works like the brain. So not in terms of deterministic, but the human brain, they say, is more associative. So you associate things and bring things together. And that's what we're trying to do. Now, the Human Brain Project did not come up with a solution, but enough people think that they can build something like that, that there is enough funding to do something. But I don't know what the status is. It's just something like quantum computing, where I believe we could see an approach that moves away from this very deterministic, very primitive plus minus multiply divide approach, and opens up a field where we could see new types of applications. That's why I mention it as a potential opportunity. Yeah. But I'm not in the details of that, I'm sorry. Okay? Thank you. Now you're relieved. 3 questions. Thank you. Now, Fabian, you have to say something.
I have to say something.
Like,
thank you very much.
Thank you for coming, and
for coming.
hope to see you next time. And
No, it would be great if we are in the same building, that we have more kind of collaboration. So I'm really happy that the Academy of Architecture and Urban Studies kind of moved here. And I think the potential is high. We already have one collaboration with Lauri and also the library. So TalTech HPC Center and XR Center. Arthur is heading, the XR Center, which belongs to Academy of Architecture and Urban Studies. Lauri Anton, the HPC Center of belonging to School of IT. So I think this is a very nice first collaboration with virtual reality, augmented reality. Uwe Wössner and Michael Resch are supporting us from Stuttgart with software, knowledge, and kind of experience, and also in hardware. And we are very grateful for this. And I stop talking now, else we are going to miss our kind of follow-up program.
Yep, okay.
But I wish you a very nice evening, and thank you for your for coming here.
Thank you.
Thank you so much.